The first thing we're going to do in this video is we're going to install an external Python library called RSA, which is also the crypto system that we're going to use. And for that, we're going to open up a command line and we're going to type pip install RSA. And this library will now allow us to generate key pairs, so public key, private key. We can encrypt messages, we can decrypt messages, we can sign messages, and we can verify messages. Now, for those of you who don't know anything about asymmetric encryption, I'm going to give you a very basic overview. The key idea is that we have public key and private key as opposed to a password. So we don't encrypt and decrypt with the same key or password. We do it with public and private keys. So the public key is used for the encryption and the private key is used for the decryption, or the private key is also used for signing and the public key for verifying the signature. The basic idea is the following. If I generate a key pair, public and private key, they belong to each other, and I can just put on my website, for example, my public key. Everyone can know my public key because that's what you use to send me a confidential message. So I put it on my website, you go on my website, you get the public key, and you say, hey, I have a secret message for you, whatever. You encrypt it with a public key, you send it to me, and the only way to decrypt that message is not with the same public key, but with the private key. So this is the corresponding private key. The only way to decrypt that message is, that is why it's called asymmetric, because you don't use the same key, is with the respective private key. So I can only, if I'm the only one that has a private key, and this should be the case, I'm the only one who can decrypt the message. And the private key is also called secret key, which tells you it should be kept secret. So this is what we're going to do in this video here, and vice versa. I can also sign a message or a document or something with a private key, making it authentic, showing you, okay, this is actually a message from me, and you can verify that this is the case because the public key can verify the signature. And the only way the public key is going to say, yes, this is verified, is if it was signed with my private key. So we're going to start here with a very simple example. We're going to just import RSA and we're going to generate a key pair. And I'm going to say public key, private key is going to be equal to RSA new keys 1024 bytes. And we can actually go ahead and just print the data that we have in here. For example, for the private key, and you can see it's just a bunch of digits. But it makes sense to export these keys into files because we want to use them, of course. We want to put them somewhere. We want to use them as files and not just keep them live in the script. We want to save them somewhere. So what we're going to do is we're going to open a file and we're going to call this file, for example, public.pem. This is the format that we're going to use, and we're going to write bytes into that file stream that we're going to call f here. We're going to say f.write, and we're going to write public key.save pk cs1, and the format is pem. Now, in this video, I'm not going to go into the explanation of what pkcs1 is, into what pem is, and so on. This video was not focused on the theory of encryption, on the theoretical background. If you want to have a video on these things, on these theoretical behind the scenes aspects and not just a practical Python tutorial, let me know in the comment section down below. Maybe I can make a video on it. But for this video, we're just going to focus on the Python application here. So I'm going to do the same thing for the private key. I'm going to change this here to private key. And when we run this, you can see we have two new files and they have the respective signatures. So begin RSA private key, begin RSA public key. This is what you would get. So this is what I would put online on my website. And the only way to decrypt something that is encrypted with this public key is by using that private key. And of course, now in this video, I show you this private key, but preferably you want to keep this secret because that's the only way that you can decrypt something that was encrypted with a public key. And that's also the thing that allows you to sign something. So if I sign something with that private key, provided that no one else has that private key, you can be 100% sure, provided that you have the correct public key, that whatever you get is from me. So it cannot be from someone else unless they have my private key. So this is what we do. We have these keys and we can now, instead of generating them every time, we can just say with open and then public pem reading bytes as sf. We're going to say public underscore key is going to be equal to f.read. We're going to copy this here and we're going to do the same thing for private so that we don't have to constantly generate new keys. Because we want to have the same public and private keys, right? Every time you generate them, you're going to get different keys, so you want to have the same pair all the time. And this is actually, I forgot one thing. This is not what we do, because by saying f.read, we essentially just read the PEM format. We have to load this using the same algorithm. So we're going to say rsa.public key .load pkcs whatever we read, and here down below we're going to say rsa.private key .load pkcs1 fread. And then we have the actual keys in our script, and we can start by encrypting a very simple message. So we can say, for example, the message that we have is, hello, my password is neural_9999, something like that. And I want to send this to someone, right? So what I would do is I would say the encrypted message is equal to RSA encrypt. I pass the message, and then of course I want to encode it into bytes, otherwise we might have some problems. And I'm going to encrypt it with the public key. So now I can go ahead and print the encrypted message, and you will see it's not really readable in any way. So you cannot really see what's in there. And we can also go ahead and just say, okay, with open encrypted.message, for example, we're going to write bytes as f. We're going to say f write encrypted message. So I can do that, and here you can see now we have this message that is completely encrypted. We cannot read it, and the only way to decrypt that message is to essentially use the private key. So I can actually say, instead of doing this, I'm just going to say open encrypted message reading bytes dot read. I'm going to delete this, and now I'm going to say clear message, and I can actually also delete this here, so you see it's not because of the script. I can say clear message is equal to RSA decrypt, and what I pass here is again the bytes, so the encrypted message that we loaded from the file, and then the private key that we have. And if I now go ahead and print the clear message, you can see that I get the byte. I get this B here. I can also decode it to not get the B here, but essentially I get the clear text message here. So you see how it works. I generate a public-private key pair. I put the public key on neural9.com, and you can send me whatever you want encrypted like this. No one else can read it unless they have the private key. And with the private key, you can decrypt the messages that someone sends with the public key, encrypted with the public key. So this is the one use case. The other use case is to sign a message. So let's say, for example, all of you guys know my public key for some reason, because already for quite a long time the public key is online. Everyone knows, okay, this is the authentic Neural9 public key. I have said it in many videos, and you know if you have that public key, it's the authentic one. So if that is the case, what I can do is I can sign a message with the private key to let you know if you read that message on your computer. You know it is not hijacked, it is not from someone else, because the only way that this message will be verified with a public key is if you have, if it was signed with the correct private key, which only I have optimally. So in a best case scenario. So let's say I have a message. I have a new account on Twitter, which is @madeupname 9987615. Hopefully this does not exist. So if you want to know that this is actually from me and actually authentic, what I can do is I can say rsa.sign, and I can sign the message here. I can encode it. I can sign the message, and I can say that I want to sign it with a private key and with the SHA-256 algorithm, which is a hashing algorithm. So I want to sign it like that. And what I get as a result is a signature. So I get the signature here, and I can say with open, I'm just going to call the file signature. We're going to write bytes as f. And I'm going to say f.write whatever the signature is. So I can do it like this. And then what we're going to do is we're going to remove this, because that is what we have done already. And what I now want to do is I want to get the clear text message, because this is not encrypted, right? I'm not encrypting the message. It can be read by everyone. The only reason for the signature is not to have a confidential message. It's to show you that it's actually from me. So everyone can read that message. It is not a problem. My goal is to show you that it is 100% from me. So what I do here is I read the signature instead of writing the signature. So I say signature equals f.read, whatever it is. And then I can do rsa.verify, and I can say message.encode. I think we need to encode the message. I pass the signature and I pass the public key. So I need to have the public key, which I know is from you, or in this case, you know it's from me. You have also the signature, and which is what I send you, and then you have the message also. And signature and message combined can be verified by the public key. You can actually print what the result is, and in this case, if you get SHA-256, that means that it is verified because you get the hashing algorithm. If the message changes, if I say, for example, now instead of on Twitter, I say in Twitter, so one simple letter changes, you can see verification failed. The message is not authentic. It's not from me. Also, if I use any other pair for the signature, so if I use, for example, let me generate a new public key here. Public key, private key is equal to RSA new keys 1024. The message is the same, but we have a different public key now. You can see verification failed because it is not verified. It's not authentic. It's not matching. So we need to have the right message, exactly the same string, exactly the same byte stream, the correct signature, and the public key, which is the correct one, with the corresponding private key that the message was signed with. So this is how you do that. This is how you guarantee that something is authentic. So those are the use cases. You encrypt with a public key for confidentiality, you decrypt with a private key to receive the message, or you sign with a private key for authenticity and integrity, and you can verify that with a